/circ because this is the LaTeX command for writing a circle, which means composability. Okay, yeah. I'm going to be talking about CIRC, and yes, I work at Espresso, but this protocol I'm going to be describing is not exclusive to Espresso. It's just an open protocol, something similar to like IP TCP. So I'm going to be presenting it as an Ethereum community member, not as someone from Espresso. So fragmentation is bad. Composability is good. I'm not going to go into why that is because many other people during the week have gone into this, but this is the general idea. But what's composability in the first place? So I'm going to give a formal definition of it, and that is that L2s are defined by their state transition function. And so composable L2s are defined by their state transition function and the state transition function of other L2s. So for example, if rollup A is composable with rollup B, then its state transition function is composable with the state transition function of B, and vice versa. And it's possible to have only composability one way. So usually when we talk about composability, we think it's two-way, as both two rollups are composable with each other. But it is possible to do it one way. Let's say rollup B did not want to necessarily be composable with A, but rollup A did. Then you can just have the first statement where rollup A's state transition function relies on rollup B, but rollup B does not rely on rollup A. And just a quick note is that they are also mutually composable. So you can have rollup A rely on rollup B, which relies on state from A, etc. And so a quick comment about trustless composability versus trusted composability. So what I just described would be trustless composability. And that means that it's impossible to finalize inconsistent data across L2s because you are fundamentally enforcing it at the state transition function level, at the definition of the rollup level. So you can cryptographically enforce it. An example of this would be something that uses a shared settlement contract where two rollups settle at the same time. So then you have trusted composability, which is still very useful, but it's not baked into the definition of what an L2 is. So this relies on some sort of economic stake or reputation in the form of like a pre-confirmation from a shared sequencer. And you do still have a small chance of finalizing something that is inconsistent across the different L2s. So an example of this would be a shared builder. This shared builder might be able to give you a strong pre-confirmation that your transaction will be atomic, but you know, if your transaction is worth more than they have staked, then maybe they'll go back on that promise. So I'm really going to focus on the trustless composability here because the trustless composability, in my opinion, is really required for things like native bridging. So if you're bridging one token from rollup A to rollup B and you're using trusted composability, like a pre-confirmation from a shared builder, that's fine, but when you're dealing with like native assets, like native ETH, I think it's really important that you make sure that it is impossible to print ETH out of thin air on a rollup. Yep, so we're gonna go with trusted composability. But first, let's talk about sync composability versus asynchronous composability, which are two kind of definitions that float around out there. So I'm gonna define them as on this graph here. So basically, async composability is asymptotic to synchronous composability. So asynchronous composability is kind of parameterized by the amount of time between your async messages. And as the amount of time between your async messages decreases, then you get very, very close to something like synchronous composability. But it's not quite synchronous, but you get very close. So for example, if you have L1 finality, that takes 15 minutes. So your latency between messages is pretty large, versus if you have 1 second latency between your async messages, that's a lot better. Yep, so async communication is asymptotic to synchronous communication. But then what's the difference? Like, what is the difference that takes like this bottom part of the line that's async and turns it into something that's synchronous? And that is how it's enforced. So asynchronous composability is not enforced through the state transition function, whereas synchronous composability is. So synchronous composability, the way it works is that you are changing the unit of atomicity to be several transactions across many chains. Whereas in synchronous composability, your unit of atomicity is just your general one transaction on a single chain. And so with synchronous composability, since you're fundamentally changing the unit of atomicity that the state transition function recognizes, it's enforced by the state transition function, whereas no matter how, you can get really, really fast async, but it's not ever going to be enforced at the state transition function level, and you have to build something on top of that to do your logic. All right, so let's look at an example about, well, like, why does that matter? Why, if I have, 1 millisecond latency between my async messages, well, isn't that good enough? And the answer is yes, that's good enough for a lot of use cases, but I'm specifically going to focus on atomicity and see how atomicity may be difficult to achieve always in the asynchronous case. So let's consider this example. These are transactions in a single chain, so we're not even talking about two chains. And we have the blue transaction. The blue transactions are a part of an atomic group of transactions. So they either both need to succeed or they both need to fail, but they're asynchronous. So the first transaction increases the price of ETH, and then in the middle, there's some transaction that says, oh, the price of ETH increased, I'm going to trade. And then you get to the second blue one, and turns out it reverts. So you need to undo, your logic of both of those transactions. But the key part is that you can't undo this middle transaction because that's not yours. So someone has already read the intermediate state, and you can't revert that. And so this is the key difference between synchronous versus asynchronous composability in practice. All right, but how do we actually get composability? So this is where CIRC comes in. So composability, you need 4 things. The first one is just a message format. That's basically, you just need a way that everybody agrees to communicate. But the last 3 are the most important, which is shared settlement, coordination, and a confirmation layer. And you need these regardless of protocol. So I'm going to talk about these in the context of CIRC, but any sort of cross-chain interop protocol fundamentally needs all of these things. All right, but before we dive into the details, well, why CIRC in the first place? Why create a new protocol? And that's because you want permissionless cross-chain messaging that's easy, like calling an API. So for example, if I'm a DEX, I can have a standard API that allows me to receive any incoming messages from any chain. And those chains or those apps don't have to have some bespoke relationship with the DEX where they have permission to call the DEX with this certain standard. People can just permissionlessly send messages across chains. And then also, a big point is that you get a unified developer experience regardless of async or sync messages. So kind of like similar to what Justin was saying earlier, the developer experience is the same across all chains and across all VMs. So the developer only needs to learn how to do async and synchronous composability with a single format, and you don't have to support all of these different types. You don't have to adapt your application every single time you want to do a new messaging format, etc. But then, well, what about existing standards? Because there are several existing cross-chain messaging protocol standards, and there's 2 main reasons. One is that most of them are too specific. They're like specific to something like an intent or specific to bridging tokens. And so CIRC is designed to be very general. And actually, you can implement these other cross-chain message passing protocols on top of CIRC. And then also, finally, the generally speaking, cross-chain messaging protocols today, they don't support synchronous message passing. So synchronous message passing, it means that you're message passing without knowing the finalized state of the other chain. So you have to enforce that the state is consistent at settlement time. And most other protocols don't allow you to do this. So these are the 2 key reasons why, there's this new protocol, CIRC. All right, so we're gonna start with the message format, and it's pretty simple. So basically, when you send a message from rollup A to rollup B, you're creating a connection or a link that says, hey, I'm linking these two transactions together. And so you have just a common interface. And the way it works is that you have these mailboxes. You have an inbox and outbox on each chain. It's implemented as a smart contract, so there's no changes to the VM required. And as long as it's implemented according to the specification, it can be implemented in any language, any VM. And then you have the actual message type. So the message consists of metadata and a payload. So the metadata is just your routing information. You can think of it like an IP protocol, where you're just telling it how to figure out who to send the message to. And then the payload is just anything you want it to be. There's no format required on the payload. And the way that these are actually mapped is that you have in your inbox and your outbox, you have a map where your metadata is the key and it points to the payload as the value. So it's a pretty simple smart contract to implement. All right, now let's go into shared settlement, which was the second thing that we needed to get synchronous composability. So all rollups, shared settlement is when all rollups are settling within a single L1 transaction on the same contract. And this is how you fundamentally get like cryptographically enforceable atomicity. And you cannot 100% guarantee atomicity unless you're settling at the same time. For example, let's say you had two rollups who were even settling in the same L1 block. Well, it means that one of those rollups can settle and the other rollup can not settle. So like rollup A could settle and say, okay, I've settled, and then rollup B could settle, and now you don't have atomicity that both of them are gonna settle. For example, rollup A may settle first, and then turns out rollup B never submits its transaction, or its transaction fails. And so now rollup A and B are not settling together. So if you want to guarantee atomicity, you need to have shared settlement. And the shared settlement, it basically does two validity checks on the rollups to make sure that they are consistent and they have consistent state between each other. So the first is it checks the execution of each rollup in regards to a certain input. So basically it takes, hey, this is the block that was sequenced and this is the order of transactions, and it verifies that the execution is correct regarding that order of transactions. And this can be an optimistic fraud proof or a ZK proof. And then finally, you also check consistency across the rollups. And this is just a quick note that if you want interoperability within the span of a single L1 block, or within the span of, without waiting to go through Ethereum as a layer, then you must have some sort of shared settlement if you want to guarantee atomicity. But again, it can also be just one-way shared settlement. All right, so then, well, how do you actually check if the mailboxes are consistent? Well, basically, you just check if they equal each other. So in the case of two rollups, it's pretty easy. But if you have more than two rollups, you would just take the union of all the inboxes and check if it's equal to the union of all of the outboxes. All right, so next we're going to go on to the third part, which is coordination. This is the third thing we need to get composability. So coordination means that you have something that can execute for both chains to figure out the data passed between it. And this is fundamentally required because you may have messages that are only sent based on the execution of previous messages. So you fundamentally have to have someone who can execute both chains to figure out what the messages are. And shared sequencers make extremely, extremely good coordinators because they do this already. They're already sequencing transactions for the rollups anyway. So as a quick example, so basically, coordination is just concurrent programming. So you can think of any sort of concurrent programming or parallel execution algorithm, and that's essentially what the coordinator is doing. And then a final note is that shared sequencers do make really, really good coordinators, but it's not strictly required that you have a shared sequencer. There's some things you can do even without a shared sequencer, where two rollups are sequenced separately. You can still enforce atomicity and synchronous composability. And so the way that this works is essentially this coordinator is creating a partial ordering. So if you have rollup A on the left and rollup B on the right, these transactions are ordered. So transaction 1 has to come before transaction 3 on rollup B because that's the order of their transactions. But what the coordinator is doing is creating a partial ordering in between them. So naturally, rollup A and rollup B, their transactions don't have any ordering between them. Like, how would you decide which one would go first if you would execute them together? So the coordinator is doing that. They're saying, hey, I'm going to execute transaction 1 before I execute transaction 2. And yep, so what this looks like in practice is that the coordinator executes both rollups, and then this execution populates the outbox of each rollup, and the coordinator just copies the outbox into the inbox of the other rollup. All right, and then finally, confirmation layer. So this is the last thing we need to have composability. And this is because rollups don't trust each other, and rollups don't trust their shared sequencers or these coordinator parties. And the L1 is the most obvious layer for it to be a confirmation layer, and that is in fact what the L1 is today. This is why people send their messages through the L1, because they don't trust anything else. But the L1 is slow, so you can actually have a new confirmation layer in here that's very fast, that can enable a lot faster composability without having to wait to go through the L1. And so the way that this works is that the coordinator or sequencer, they take your block, they decide the order of transactions, and they send it to this confirmation layer, which gives them a certificate that it's confirmed on the network. And then what happens is rollup A and rollup B will both read from the same thing on the confirmation network, and they'll prove execution, either through a ZK proof or through a fraud proof. And then they'll post these proofs to the L1 shared settlement contract, and then you'll check equivalence. So in practice, the way you do this is you take the hash of inbox or of mailbox A, and you compare it to the hash of mailbox B. And the important thing here is that in the confirmation layer, both of rollup A and rollup B are reading from the same source of truth. Like, that's the important part, because what you don't want is for, say, your shared sequencer to send one block to one rollup and a different block to another rollup, because now it's easy for the shared sequencer to be malicious and cause some reorg down the line. But the confirmation layer ensures that everybody is reading from the same information, and the smart contract, the settlement smart contract on the L1 will check to make sure that the data that's being settled is the same data on the confirmation layer. All right, so, well, what are these properties of CIRC? Like, why is this a good protocol to use? Several things. So one is that proving is done at the end. So if you can't prove very quickly, you don't have to wait on proofs between your messages for the L1. You can send your messages as quickly as you want, even synchronously, and you can just prove it all at the end in one big batch. The next thing is that composability is really only bounded by execution time. So when you are actually sending messages between rollups, that's only bounded by like literally the time it takes to sequence and execute those transactions. Since you're proving at the end and not on the critical path, you can compose as fast as you can execute. And then also, it works with any DA layer or proof system as well. And another important thing is that this requires no VM changes, which is very important because it means that all rollups today could literally implement this tomorrow, essentially. It's just a smart contract. And the flexible messaging format means you can build more specific messaging protocols on top. So if you recall, the payload has no requirements, it's just data. So you could, for example, you could build an intent-specific messaging protocol on top of that by requiring that that data field has some particular format. Also, it allows parallel proving, and everything is enforced at settlement time, which means that you are guaranteed that your atomicity is maintained, which is different than something that is crypto-economically enforced by stake. All right, so that is CIRC. That is the Coordinated Inter-Rollup Communication Protocol. And there will be an ERC out soon that kind of describes this in detail. Again, it's an open protocol. You don't have to use Espresso to use it. It's just meant to standardize this, because right now, even if we have the infrastructure to get interoperability between L2s, if everybody is using a different standard, it's obviously not going to work out. So I think this is really analogous to IP TCP, that you can build more specific stuff on top of it, but everybody is fundamentally routing messages and communicating and coordinating in the same way. And with that, yeah, that's it. Thank you.
We have time for questions. Yeah. Does anyone have any questions?
So you mentioned that this could be used for both synchronous and asynchronous communication. So to a dev, right, those are very different things, because in a synchronous, with synchronous communication, you can revert, right, all the way back to the beginning. So if this can work for both, how does a dev, program for both scenarios?
Yeah, so I think the way you program, it's actually very similar. So you're not like locking a resource in the sense of concurrent programming, you're just sending messages. So the way that you do that in a synchronous way would be that you send a message to the other chain, and then you immediately wait for a message back in that same transaction. If you don't get that message back, then that entire transaction will revert, because the transaction is the unit of atomicity. And if you were doing it asynchronously, you would just send the message, and then you wouldn't wait for it to come back. So it's a pretty small difference from the developer standpoint.
So when you actually write application on top of CIRC, you have to understand, okay, am I doing this asynchronously or synchronously, and write applications differently. Okay.
Yes, so yeah, you do have to understand if you're doing it, although I imagine there'll probably be libraries that abstract that out for developers.
Thanks.
Thank you.
Who's running the confirmation layer, and like what happens if it like reorgs?
Yeah, so the confirmation layer should be something that's very secure and is not going to reorg. So you would probably want a confirmation layer with very fast finality. So unlike Ethereum, it literally comes to finality and will never reorg after like a few seconds. But if you think of the L1 as the confirmation layer, Ethereum has never reorged after Ethereum finality, and so you don't really have to worry about that.
But if you go via Ethereum, then it's slower. So if you want faster, you're saying we do one layer below, but then we figure out like something that's credibly neutral. Is that correct?
Yeah, so your confirmation layer would need to be like also a decentralized, economically secure network.
Thank you.
Hey, thanks for the talk. My question is, how does the data between the confirmation layer and the L1, how is that shared? Like, because it seems like it's important to know the state of those two.
Yeah. So that's a good point. So the confirmation layer actually also settles to the L1. It's not a rollup itself, but it settles its state to the L1. So in the L1 contract, you can read, basically you read the settled state from the confirmation layer on the L1.
How complicated would it be for the coordinator, and who would likely run the coordinator, like a super builders? Like, imagine the case for like 5 or 10 rollups.
Yeah, so it would probably be someone who has the kind of sophistication as a builder does today, although it doesn't actually need to do any sort of MEV. So if your coordinator is a shared sequencer, then it's just the shared sequencer who runs it, which is kind of similar to the builders today. If your coordinator is not the shared sequencer, because you're using separate sequencers, then all they need to do is execute. They don't need to know anything about MEV strategies because they can't reorder anything. So you just need someone who can execute for both chains. But generally, yes, it'll have to be a more sophisticated party, probably.
Like will the shared sequencer have some sort of integrated with the coordinators or something?
Integrated with what? Sorry, I didn't catch that.
With the coordinator?
Yeah, so literally, if you have a shared sequencer, they're just the same thing. You actually don't, the shared sequencer is the coordinator, and they just do the coordination at the same time they're sequencing. It's only in the case where you have separate sequencers that there are separate parties.
Oh, thank you.
Do we have other questions? Otherwise, I'll go right here.
Just a quick question. Who's building this and how are they going to coordinate?
Building the protocol.
Yeah, the entire thing.
Yeah, so we are going to have an ERC up, and then Espresso can potentially build some of these smart contracts as a public good, but it's also open to anybody in the community who wants to contribute to it. Really, the only work that needs to be done is these smart contracts and the shared settlement contract. So it's not a whole lot of work.
Well, actually, so this goes into my question, which is like maybe talk a little bit about how, like in ERC, a standard is not, there's a difference between a standard and a protocol, right?
Yes.
So a standard is like a general, it's a standard that many different protocols can conform to. So maybe talk a little bit about how CIRC, which I understand, well, I also know about it because I worked on it with you, but I also understand from your talk, or other people may have understood from your talk, that this is super general in terms of, that you specify that, there's this sort of mailbox abstraction, but that could be implemented in multiple ways, perhaps, right?
Yes.
And then there's this, shared sort of settlement procedure, right? But you were vague on that, and it could be implemented directly on the L1, or it could be implemented in some kind of integrated fraud-proof mechanism, which may be related to how Mark over there is doing things, right? And or it could be implemented in some kind of proof aggregation system, like what the AggLayer is working on. So maybe talk a little bit about how CIRC is more of a standard than like a specific protocol, and how it can kind of unify these different protocols. And what is the goal of standardization? Is it so that application developers can write applications, and whether they're deployed to the superchain interoperability cluster or AggLayer, they work just the same?
Yes, so that is correct on the second point. The point of this standard is that so you can develop interoperability between any sort of cluster, any sort of VM in the exact same way. And this is really important because you have devs that are going to you have devs on, the superchain that are going to want to have interoperability with something like an Arbitrum Nitro chain. And if they can share the same APIs, this is so much easier than having to support, all variety of different message formats, et cetera. So that's the value in the standard. And then why is CIRC a standard and not a protocol? Well, because CIRC is really what it's doing, its core part is it's defining the message standard and a very lightweight description of how you could use it for synchronous or asynchronous composability. It does not force you to use it for synchronous composability. You could not do that at all. It doesn't force you to use it for bidirectional composability. It's really just a description of a message format and a procedure that you can use to get composability, but it's very vague and general.